This video will cover similarity and dimensional analysis. You will learn how small-scale models, such as the one you see here, could be used to predict the fluid forces of the actual prototypes that they are modeling. As a quick review, lift and drag are summarized here. Recall that the coefficients of lift and drag are dimensionless and can be determined experimentally. Such experiments could look like what you see here. Now, how do aerospace engineers determine the coefficient of drag of something like this? The space shuttle is massive, and it would have been impractical to build actual prototypes of various designs of the space shuttle to determine lift and drag characteristics of this vehicle. What engineers do is create scale models of very large prototypes and test them in a wind tunnel. But how on earth could measurements on a small scale model be used to predict the lift and drag forces on the real thing? How is the test shown in this picture even valid? Here's how it's valid. The concept of similitude is used so that measurements made on one system, such as a model in a wind tunnel, can be used to describe the behavior of other similar systems, such as an actual space shuttle at launch. Let's go into similitude, which is also called similarity. Imagine that you have an actual prototype, such as a large wing, that will be undergoing a certain flow condition. You can make a much smaller scale model of the large object and subject it to a different flow condition. The smaller model at the different flow condition could then be used to predict the characteristics of the larger object and its flow condition if the model and object have similitude. Models have similitude with the real application if the two share 1. Geometric similitude, in which all body dimensions of the actual object and the model have the same linear scale ratio. If you've ever been in a toy store or a hobby shop, you can find scale models of a myriad of vehicles. Here, you see an actual F-14 on the left, and on the right, you can see a scale model of the F-14 that you can snap together and play with. The scale model has the same linear scale ratio in body dimensions as the actual aircraft. However, geometric similitude is not enough. I repeat, geometric similitude is not enough. You will also need kinematic similitude, in which the velocity ratio is constant everywhere in the flow fields of the model and actual objects. Now, dynamic similitude must also be maintained between the actual object and the model. This means that forces are in the same ratio and have equivalent directions between the real thing and scaled model. The ratio of lift forces on the real thing and the model must also equal the ratio of drag forces between the real thing and the model. Therefore, to achieve complete similarity between the model and the actual object, geometric, kinematic, and dynamic similitude must be maintained between these two systems. Similitude between an actual object and a model automatically follow if all the important variables are included in dimensional analysis. Dimensional analysis is a compacting technique used to reduce the complexity of experimental programs and at the same time increase the generality of experimental information. It is a method for reducing the number and complexity of experimental variables that affect a given physical phenomenon. For example, suppose we are interested in the flow of water through a long, smooth-walled, horizontal, circular pipe. An important characteristic of this system that would be of interest to an engineer designing a pipeline would be the pressure drop per unit length that develops along the pipe as a result of friction. This seems simple, but it generally cannot be solved analytically, even with the aid of supercomputers if you do not have experimental data. So, experiments need to be conducted. The first step in planning an experiment for this problem would be to decide on the variables that will have an effect on the pressure drop per unit length. In this case, it is the pipe diameter d, fluid density rho, fluid viscosity mu, and the mean velocity of the fluid flowing through the pipe, v. Now, it's very important to develop a meaningful and systematic way to perform an experiment. One way of determining the functional relationship between the pressure drop and the various factors that influence it would be to change one of the variables and hold all others constant and measure the corresponding pressure drop. For example, we could hold pipe diameter, fluid density, and fluid viscosity constant and vary the velocity and measure the corresponding pressure drop. Such a test would result in a plot that is only valid for the specific pipe and the specific fluid used in the tests. This experiment would not give us the general information that we are looking for. We would need to conduct additional experiments. We could hold fluid velocity, density, and viscosity constant and vary the pipe diameter and measure the corresponding pressure drop. This set of experiments would result in the plot shown to the right. We could then hold the pipe diameter, fluid velocity, and fluid viscosity constant and vary the fluid density and measure the corresponding pressure drop. Finally, we could hold the pipe diameter, fluid density, and fluid velocity constant and vary the fluid viscosity and measure the corresponding pressure drop. We would now have some idea of the relationship between the pressure drop and the various factors that influence it. But let's stop for a moment and think about how complicated this set of experiments would be and the large number of experiments that would have to be conducted to get the necessary data. Some of the experiments we have just discussed would be very difficult to carry out. How could we vary fluid density while holding its viscosity constant? That's a tough one. Even if you are able to figure out how to do that, how could we combine all of this information to obtain the desired general functional relationship between the pressure drop, pipe diameter, fluid velocity, density, and viscosity that would be valid for any similar pipe system? There has to be a better way, and the good news is, there is. Here is a much simpler approach to this problem. Rather than working with the original list of variables, we can collect them into two non-dimensional combinations of variables called dimensionless groups, which is shown here. Instead of having to work with 5 variables, we can now focus on just 2. An experiment could be carried out where rho Vd over mu could be varied and d delta p sub L over rho V squared could be determined. The results of this experiment could then be represented by a single universal curve shown here. The curve shown here would be valid for any combination of smooth-walled pipe and incompressible Newtonian fluid. We could generate this curve by choosing a pipe of convenient size and a fluid that is easy to work with, such as water. We would not need different pipe sizes or other types of fluids. The experiment would be simpler and easier to do and would cost a lot less. Therefore, dimensionless products are useful in the planning, execution, and interpretation of experiments, and we will make good use of dimensionless products in Similitude. In summary, Similitude is used so that measurements made on a small model of a system can be used to describe the behavior of an actual larger system. Complete similarity between a system and its model requires geometric, dynamic, and kinematic similitude. While this sounds complicated, similitude between a system and its model will automatically follow if all the important variables are included in the dimensional analysis. We began our discussion of dimensional analysis in this video, which is a method of reducing the number and complexity of experimental variables that affect a given physical phenomenon. We will continue our discussion on dimensional analysis in the next video. Now let's take a quiz. Here is your question, and the choices are shown below. Please pause the video, give the question some thought, and select the correct answer. Unpause the video to see the solutions. The correct answer is D. You need geometric, kinematic, and dynamic similitude for a model to have similitude with the real thing.